Let us talk about the different properties of the matrix operations. So, when we're going to talk about matrix operations, we have already talked about matrix addition, scalar multiplication, and matrix multiplication. Putting them all together, we can form the algebra of matrices. Take note that when we have an algebra, we are studying the structure of that specific object, more like studying its language. We were concerned last time with the mechanics of the three basic matrix operations: matrix addition, scalar multiplication, and matrix multiplication, which we mentioned just a while ago. Now, we are going to develop the algebra of these matrices, meaning it's not just performing the basic operation, but what are the properties governing these operations. This algebra share any but not all of the properties of the algebra of real numbers, meaning there will be instances wherein the algebra of matrices, when we do our operation, seems like they are just how we operate on real numbers, but not all of them. Now, we begin with what are the properties of matrix addition and scalar multiplication. And this is a theorem. So if we are given A, B, and C are m by n matrices, and C and D are scalars, then the following properties are true. The first of, A plus B is equal to B plus A, or commutativity in addition, which we have already actually seen in action last time. So, next up, we have that A plus B plus C is equal to A plus B plus C. Or, when we're going to add three matrices, it doesn't actually matter the order of adding them. You're just going to give them the same result. And that is associativity. Now, there's also associativity in scalar multiplication. If we're going to multiply two scalars to a matrix, it's the same when you multiply first the two scalars, then multiply that product to the matrix, or you multiply first one of the scalars to the matrix, and that new matrix formed will be multiplied to the next scalar. Now, we have also multiplicative identity, wherein if we multiply 1, the scalar 1, to the matrix, then we're just going to get the original matrix. And then, if we would have to multiply a scalar to the sum of two matrices, it's just the same as multiplying the scalar to each of the matrix first, then adding the resulting matrices. Or the other way around. If you would like to multiply the sum of two scalars to a matrix, you can also first multiply this scalar to the matrix first, and this scalar to that one, and then that's the time that you add them. Now, these properties are governing the way we perform our operations, but that does not necessarily mean that you have to strictly follow whatever these properties hold when you perform the operation. Let's take a closer look on what I meant. So, we are asked to evaluate the following expressions. Now, let's take a look at the first one. At the first one, we have three matrices to add. According to associativity and addition of matrices, we can either add this two first, or we can add this two first. It doesn't really matter. So, what matters is, for you as the one who's solving, which one would be more efficient on your end. So, let's try to work out this one. Any will follow, and it comes to no surprise that some of you might think if we can just immediately add them all, which also something we can do because that is a consequence of the associativity over addition. So if we're going to add all of them, we can just simply have negative 5 plus 7 plus negative 10, which is negative 8, 0 plus 1 plus negative 8, which is negative 7, 3 plus negative 2 plus 14, which is 15, and negative 6 times negative 1, negative 6 plus negative 1 plus 6 is negative 1. Now, on your own, try if you would like to test this one first, add this two, then the third one, or add the second and the third one first, then the first one. We are sure that we're still going to get the same resulting matrix. How about the second one? In the second one, we see that we have a matrix here multiplied to the scalar -1. Then we add it to a sum of a matrix, but both of them are multiplied to 1/6. Now, we are told that this, oops, sorry, it's not seen. We are told that this can be done in two ways. First, you can add first these two matrices, then multiply to 1/6, or you can distribute the 1/6 and then add the two matrices. Whichever method you prefer will work. Now, in doing so, what I will be doing is I'll be distributing the 1/6 to illustrate that property. So therefore, for our second item, I'm still just going to copy the first one, which is negative of the matrix 4, 11, -2, -1, 9, 3, plus I am now going to multiply 1/6 to this matrix. 1/6 multiplied to -5, -1, 3, 4, 0, 13. Then add it to 1/6 multiplied to the other matrix containing the elements 7, 5, -9, -1/6, and -1. This will then result to, oops, sorry. Let's pull that up. There you go. This will now result to, I will now also distribute -1. So this will become -4, -11, 2, 1, -9, -3. Added to, we have -5, 6, -1, 6, 3, 6, 4, 6, 0, and 13 over 6. Then, we can also have the other one, 7, 6, 5, 6, -9 over 6, -1, 6, 1, and -1, 6. Oops, sorry. Let's fix that. -1. There you go. -1 over 6. Adding them all together now, we're now going to have -11 thirds, -31 thirds, 1, 3 halves, -8, -1. Of course, this addition part is left to the viewers as we were able to do that in the first item. So, it is a similar case in the third item here wherein first, you can either subtract these two matrices or multiply 4 first. We're going to still get the same result. And that result would be the following matrix. This will be equal to, after you perform all of this will be equal to -24, -4, 12, -12, 32, and then 12. So it's either you can subtract these matrices first or multiply 4 to both matrices and then subtract. You should be able to get the exact same results. So, the following properties gave us guidelines on how we can better manipulate or find an efficient way for ourselves to perform operations on matrices, specifically matrix addition and scalar multiplication.